So recall that in the last few lectures, we talk about theory and algorithm for solving linear programs and nonlinear programs and so forth. And then in the next few lectures, including this lecture, we will start talking about mixed integer linear programs and mixed integer nonlinear programs. Right? Of course, we will talk about theory, algorithm, and so forth. But then we will start with something more intuitive, which is how do you model problems that involves discrete and continuous decisions. If your research is not related to algorithm or theory, then this probably is the most important lecture for you because that teach you some toolbox to model problem. Right? If you have a problem statement, let's say a supply chain problem or some design problem in chemical engineering, how do you convert your domain knowledge or the logic you want to model into mixed integer constraints? Then you can use the commercial solvers to solve these type of problems. Right? So the major techniques we covered in this lecture is how do you convert logic propositions, right? So domain knowledge represented by logic. For example, if I do this, I don't do that, and so forth, right? How do you convert those logic decisions into 0-1 variables, right? But before that, we will finish a few things about nonlinear programming before we go to mixed integer linear programming. Just a few notes related to modeling nonlinear programming problem. Some of these ideas apply to linear or mixed integer linear programming problem as well. It will give you some good guidelines on how to come up with good models, right? Of course, you could, nowadays the solvers are really good. Even if you have a very bad model, the solver may still be okay in solving those bad models. But it's better to help the solver a little bit by creating good models, right? So guideline 1 is it's important to try to specify lower and upper bounds on all the variables, right? If you know the optimal solution is between some upper bound and lower bound based on maybe physics or based on your domain knowledge, better to specify all the bounds on all the variables. And the upper and lower bounds should be as tight as possible. By as tight as possible, I mean the XU minus XL should be as small as possible, small enough such that you are not eliminating any optimal solutions. Right? You could use those variable bounds to eliminate some solution you already know that are suboptimal. Right? Intuitively, by having tighter variable bounds, will shrink the feasible region of the problem. Right? In some of those algorithms, especially the algorithm we will cover in the second half of the semester on global optimization for non-convex problem, the variable bounds is probably one of the most important factors that determine how fast the algorithm will converge. Right? So it will become more clear in the second half of the semester. But even for convex problems, specifying variable bounds is a good practice. Okay. The other guideline is if you can convert some inequality constraints, some nonlinear inequality constraints into linear ones, always convert them to linear inequality. Right? That's very simple because linear problems are usually easier to solve than nonlinear problems. Here, it's an example. If you have the ratio of x1 and x2 less than or equal to 2, where x2 is greater than or equal to 0, you can see very easily you can convert this to a linear inequality, right? Not equality, inequality here, right? Just by multiplying x2 on both sides of the inequality, then you get a linear inequality. Okay.
So shouldn't we have x2 greater than 0 in terms of like eliminating x2 divided by 0 from the original problem?
Yeah, so you have x2 greater than or equal to 0.
But we have x1 divided by x2, meaning x2 equals 0 is not feasible.
x2 equals to 0 is not feasible.
Because we do x1 divided by.
Yeah, of course. X2 equals to 0 is not feasible
so
because.
In the second formulation, should we have x2 just greater than 0 rather than x2 greater or equal?
Yeah, so you cannot specify greater than in an optimization problem based on what is that called? Maybe Weierstrass theorem or something like that. So if you have something greater than or equal to 0, you can always find a number that is as small as possible, right? That is close to 0. That is within the numerical tolerance. Okay.
So
yeah.
Can it cause any issues or not? I mean, there's like reformulation that in the second case we have a solution. What is it? Like all negative x1
yeah.
and x2 equals to 0.
Right. So if you that's a good point. If you think about, let's say x2 approaches the limit, right? If x2 approaches the limit to 0 here, this ratio has to be less than or equal to 2, right here. I see. So you are talking about
we in the second inequality we can have a solution where x2 equals 0, right?
Yeah.
And in the first one, probably that shouldn't be possible.
Yeah, you have a good point. Yeah. In the first one, it is not. Yeah. You have a good point. I think you are right. Yeah, but then.
I don't know. Maybe it's not an issue in terms of like the optimization problem in general. Right?
Yeah. So yeah, this divided by 0 should be could be an issue for the first problem. Maybe that's another reason you want to formulate it as a linear problem rather than a nonlinear one. Right? Since the logic you want to express is x1, the ratio of x1 and x2 is less than or equal to 2. Right? So then in this problem, even if x2 is equal to 0, 0 and 0 is a feasible solution for this problem. For the first problem, it will have numerical issues, right? If both x1 and x2 goes to 0. So I think that could be another reason you want to formulate as a linear inequality. Okay, yeah, we can discuss more if you have some other thoughts. Okay, so then the other modeling guideline is to scale the numbers. If you have x1 between 0 and 1, x2 between 0 and 10,000, then this problem could be U-conditioned since these two numbers are in different scale, right? So what you can do is to define a new variable z, which is dividing x2 by 10,000. Then you can have the two variables in the same scale. Basically, you can just get rid of x2, and whenever you have x2, you replace that by 10,000. X2 over 10,000. Then there is something called condition number of a matrix. Maybe you guys have heard about this in previous lecture, right? When you have a linear system, AX equals to B, when will this linear system have numerical issues? If the condition numbers definition is the largest singular value divided by the smallest singular value, right? So if the variable have very different scales, the condition number is big, right? And then it is easy to cause numerical issues. That's one of the reasons you want to scale the numbers such that they are roughly in the same order of magnitude. And then you can also warm start nonlinear programming algorithm. Some of the solvers allow warm start. By warm start, I mean if you have a good guess of a feasible solution, maybe based on your experience or some heuristic, you already know a good solution for the original problem. Then you could initialize the variables using the initial guess you have. And some of the solvers do take the initial guess, like IPOpt allows warm start, but some of the other interior point solvers, like Mosaic, doesn't allow warm start. Okay, And then linear programming solvers like Cplex and Groovy are also amenable to warm start. Right? If you provide the optimal solution, it will be immediately certified by the linear solvers. And usually the LP solvers are easier to warm start than NLP solvers because you can think about the algorithm. The simplex algorithm can benefit from a good basic feasible solution. It can be immediately satisfied by checking all the basic feasible direction, the reduced cost, right? But the nonlinear programming solvers usually rely on primal dual solution, right? If you just provide a primal solution, it does not have a dual warm start, right? So it's not as easy as linear programming solvers. Okay, so how do you do warm start in Pyomo? Here's a trivial example to show you how to do warm start in Pyomo. Let's say your initial guess for y1, y0 and y1 is 1, 0. You choose Cplex as a solver. When you solve the problem, you could do opt.solve warm start equals to true. Then it will take the initial value you provide it to the solver. Okay. Yeah, so that's all I want to talk about for nonlinear program modeling. Okay, any questions here? Yeah. Now let's start discussing mixed integer linear programming, where the definition is you have continuous variables represented by x, some integer variables represented by y. Right? They are of different dimensions. Let's denote them by n1 and n2. So when y represent integer variables, right? But in most of the problem, the integer variables are binary variables or 0, 1 variables. In literally all the integer programming applications, the integer variables are binary variables. The reason is if you have general integer variable, right? So let's suppose in a diet problem, right? Well, we solve a linear programming problem, say how much milk, apples, eggs, and then bread you should consume per day in order to satisfy your nutrient requirement. Remember that problem, right? We solve that problem as a linear programming problem instead of saying enforcing integer constraint on the number of eggs, apples, and so forth, right? The reason I told you at that time is maybe you can cut an apple by half or by 1/3 in practice. But besides this practical reason, there is a mathematical reason for solving that problem as a linear programming problem. Because if you have general integer variable, let's say the number of apples you consume can be between 0 to 10, right? And if you solve the linear program and just do a very simple rounding, for example, the linear program gives you 5.3 apples to consume. You round it by 5. The solution wouldn't be too different than enforcing the integer, right? Because it's from 0 to 10 and you do a rounding, the error is relatively small if you solve a linear program and then do the rounding. But if you have some problem that represent logic decisions, right? So if I choose a reactor A, then I will not choose a reactor B in my chemical plant. Right? This is a very hard logic condition. You cannot say if I choose half a reactor A, then what happened to reactor B, right? So in those logic conditions, the binary variable cannot be relaxed. Right? If you relax those, you have a solution that doesn't make any sense. So that's why integer programming is really meaningful when you have logic decisions. If you have general integer decisions that describe a quantity, you can as well just relax them. It doesn't matter that much. Okay. So now for most of the algorithm I talk about, we will focus on 0, 1 variables, right? We would not focus on general integer variables for that reason. Of course, it is still NP hard to solve this problem, and there are many applications in engineering, healthcare, logistics, machine learning, and so on. Modeling is non-trivial, and the solution time of MLP solvers is very sensitive to how well you model the problem. Okay, I will show you how to write a good model in this lecture, and then in the next few lectures, we will talk about algorithm. And after you study the algorithm, then you can appreciate more about good modeling strategies. Okay. So let's start with some simple exercise to build our intuition before we introduce the theory behind that. Okay. Again, so we will use binary variable to model logic. Right? If yj is 1, that means j is true. If it's 0, then we say j is false. Then how do you model this condition? At most, one of y1 and y2 is true. Right? You might tempt it to model it as y1 times y2 equals to 0. Right? At most, one of them is true means either y1 is 0 or y2 is 0. Right? Their product is 0 for that logic condition. But the thing is that this model is nonlinear, and it is not MILP representable. Right? You have the product of y1 and y2. So how do we linearize this y1 times y2 equals to 0? A very simple linearization is y1 plus y2 less than equal to 1. Right? Because they cannot both equal to 1. If they both equals to 1, then the addition will equal to 2. Right? So therefore, you have y1 plus y2 less than equal to 1. They are equivalent. Okay.
And will both be 0 in this case?
Yes.
Even if you have to choose one, like if it's a one or the other decision?
Yeah, so here it says at most one of them is true, right? It can both be false, right?
Okay.
Or they can both be
But
0.
That won't always be true, though, right? Like if you have to choose between two things. Like if
Right.
you were trying to like say either reactor A or reactor B.
Yeah, so that's a different, yeah, so that's a different logic, right? That's an all logic, not at most one type of logic, right?
Okay.
This is like at most one is true. But what you are saying is either y1 is true or y2 is true, but they cannot both be true, right? That's exclusive. That's called exclusive all. We'll talk about that later.
Oh,
Okay,
gotcha.
yeah. Yeah, so now why do you want to model it as a linear constraint? The reason is because solving integer program rely on something called continuous relaxation. Continuous relaxation means you relax the binary variable to be a continuous variable between 0 and 1. Okay, and then solve that continuous relaxation. You will see that more in the next few lectures. Here's a geometric intuition for why you are modeling them as a linear inequality. Right? So if you consider the continuous relaxation of y1 times y2 equals to 0, right? If you relax y1 and y2 as a continuous variable between 0 and 1, then y1 and y2 equals to 0 is this region here denoted by the this thick black line here. Right? It's these two lines here. Right? And clearly it is a non-convex region, even if you relax the binary variable to be 0, 1. But if you consider the continuous relaxation of y1 plus y2 less than equal to 0, less than equal to 1, then it is this triangle area here. It is a convex region. Right? And then you can solve it as at least a continuous relaxation can be solved as a convex problem. Okay. Now, here I'm introducing a very important concept in mixed integer programming called big M constraints. So what's the motivation of doing that? Right? Suppose you want to represent the condition if y1 equals to 1, right? So let's suppose y1 represent a logic decision. If y is true, then I want to enforce these equations. Since most of the audience are chemical engineer, I will use a very simple chemical engineering example. Suppose y1 represents you are installing a reactor, right? And then h of x represents a constraint, like the physical conditions in that reactor, like mass and energy balance. What goes into the reactor has to be equal to what goes out, right? If you are installing a reactor, then you need to enforce mass and energy balance on that reactor, or some kinetics, right? Those equations can be represented using Hx equals to 0, right? Since usually the mass flow are continuous variables. Okay, so that's sort of a simple example of why we need to do that, right? And then how do we model that, right? A simple way to model that is y times h of x equals to 0, right? Why this is the case? Because if y equals to 1, then you basically have hx equals to 0, right? When y equals to 1, you have to enforce this constraint hx equal to 0. But if y equals to 0, right, what happens is you basically have 0 equals to 0, right, when y equals to 0. So of course this equation trivially hold when y equals to 0. Okay, so what's the problem with this formulation, right? It's the same problem as what we discussed before when you have y1 times y2, because if hx is a linear equation, right? Suppose you have let's say mass balance, right? It's a linear equation. Then if you formulate this problem as y times h of x equals to 0, then you are going to have nonlinear constraints here, right? And that won't be MILP representable since you have the product of y with some continuous variables. Okay, so so we don't want to do that that way. Then you may ask, what will be the alternative way of formulating this problem, right? So that's why we need something called big M inequalities. So here, M, you can think about M as a very large number. How large M is, we will talk about that later, right? So for now, let's just think about F as this big M parameter as a very large number, okay? So we can formulate the problem in this way: minus M times 1 minus y less than or equal to h of x less than or equal to M times 1 minus y. Okay, so let me explain that step by step. So usually when you try to interpret those logic conditions, you only need to think about two conditions, right? When y equals to 1, what happens? When y equals to 0, what happens, right? If both conditions make sense, then you are good, right? So let's first think about when y equals to 1, what happens, right? When y equals to 1, 1 minus y equals to 0, right? So this guy is 0, and this guy is 0 as well, right? So when y equals to 0, it reduces to h of x equals to 0. That's what we want to model when y equals to 1, basically enforcing the constraint hx equals to 0. The tricky thing is what happens when y equals to 1, when y equals to 0. Right? When y equals to 0, then you have minus m less than or equal to h of x less than or equal to m. Basically, it is saying the value of h of x is between minus m and plus m. Right? M is a very large number. Right? So that means if you choose a big M that is very large, right? Suppose the value of x is bounded, right? Like I said, whenever you model a problem, all the variables are usually bounded, right? Suppose x is your mass flow rate into a reactor. The flow cannot be larger than, let's say, the pipes you have in a chemical plant, right? The length of the width of the pipes. So you can bound all the x variables. Therefore, you can have a non-trivial bound on the value of h of x, right? So there exists a sufficiently large M that will make this inequality redundant, right? If h of x is bounded in practice, okay? But then when you model the problem, you should pick M that is large enough such that you do not eliminate any optimal solutions. But in the meantime, you should make the M as small as possible. Okay. The reason is when the value of M is too large, then the feasible region will be too large for the continuous relaxations. We will show you a picture to demonstrate that. Okay. Yeah, let me stop here and see if there are any questions. Yes.
if you have a more dynamic constraint, like x1 needs to be greater than x2,
Mm-hmm.
does that cause any like additional problems to something like this? Or what effects would those types of constraints have?
X1 greater than equal to x2. Why would that affect this? So in addition to this big M condition, you have some other constraints, you say?
Yeah, so I was wondering if there's any interplay between constraints like that.
Oh yeah, so that's a good question. I mean, from a modeling perspective, there wouldn't be much impact. But from an algorithmic perspective, there will be some impact. Yeah, right. It will be more clear when we talk about things like cutting planes or how to come up with a good relaxation and so forth. From a modeling perspective, you just want these constraints to hold. This will not affect other constraints, right? If X has to satisfy other constraints, you can just add those additional constraints. Okay, yeah. Any other questions?
Can H be a nonlinear function?
Yeah, H can be a nonlinear function, right? You need to derive the right big M value for that nonlinear function, right? From the bounds on the X variables, when H is nonlinear, then you should derive a non-trivial big M, right? Sort of a rookie mistake in modeling mixed integer programs is that when students learn about these big M constraints, then they know that you can set a big M that is large enough, right? So then they set a big M that is 10 raised to the power of 6, right? And then the model becomes super slow to solve. The reason is you should choose an M that this constraint will hold trivially, but not that trivial, right? You shouldn't choose 10 to the raised to the power of 6, but using Hx to derive a bound that is as tight as possible.
So if you know the bounds of what your Hx are, when you're doing your big M, should the M be exactly those bounds, or should it be like a magnitude larger than what you think Hx
Yeah, that's a good point. So if you have the bounds on X, right, and then you know the bounds of Hx, and you know the optimal solution will not exceed those bounds, then just choose exactly that, right? Yeah. Sometimes you can even get even tighter bounds than using the bounds of X and H of X by adding some other domain knowledge to the problem, or based on some other equations, you could derive an even tighter bound. Okay. Yeah. Yes.
So when we use some like Python to formulate our mixed integer linear programming,
Yeah.
we can do like using a binary variable multiplied by our hx, right? And
Yeah.
Python will automatically translate to this form.
Yeah, that's a good question. So let me rephrase the question so that all the other people also know this answer, right? So you're asking, what if you model a problem like this in Python, right? Yeah, it is fine if you choose the right solver. For example, if Hx is a nonlinear function, right? Then you formulate something like Hx times y. Then that becomes a mixed integer nonlinear programming problem, right? If you pick the mixed integer nonlinear programming solver, what it does is it will automatically translate your constraint into some linear programming relaxation. That's what we will talk about in the second half of this class, right? So it's not Python automatically translate the constraints into a linear form. It's a solver's Python used that translate the constraints. Okay, but then if a solver can only solve mixed integer linear programming problem, and Hx is linear, you have to use this rather than this, right? Otherwise, the solver will not take problem of that quadratic form. Okay. Now, let's give a few more examples on how to model problem using binary variable, right? Now let's assume y of j is a set of binary variable that represent whether you are selecting the j's item or not. Right? Then if you want to say I want to select at least one, then it is equivalent to the summation of y of j greater than 1, equal to 1, right? And if you want to represent select exactly 1, that's a summation of y of j equals to 1, right? Similarly, you want to say select not more than 1, then the summation will be less than or equal to 1. It should be a very simple logic constraints. Now, how do you represent if-then conditions? Right? If I select reactor A, then I don't select reactor B. Or if I select reactor A, I need to choose distillation column C. Right? Some of these logic conditions, how do you represent that using 0, 1 variable? Right? The logic condition is, say, yk implies yj. Right? If you select k, then select j. Then this condition can be written as this linear inequality constraint saying yk minus yj less than or equal to 0. Right? So this can be easily verified because when yk equals to 1, it will false yj equals to 1. Right? When yk equals 1 is like I'm selecting yk, then yj has to be selected. But then when yk is 0, right? You don't know you should choose yj or not. Then yj can be either 0 or 1. Right? So if yk is 0, then this reduces to yj greater than 0. Then yj can be either 0 or 1. Okay. And then a different condition is saying if and only if. Right? I select j if and only if I select k. Right? So that condition is slightly different. That will be yk equals to yj. Those are two different logic conditions. Now, there's something else called disjunctions that occur quite common in some of these applications. Right? So let's consider what is so-called a disjunctive constraint, meaning that either f1 x has to be less than or equal to 0, or the second constraint has to be less than or equal to 0. f2x has to be less than or equal to 0. Right? So that means either the first constraint or the second constraint has to be satisfied. Right? So when will this occur is, let's assume you have a, let's say, chemical process design problem. You should select either reactor 1 or reactor 2. Right? When you select reactor 1, then you need to enforce mass and energy balance for reactor 1. If you select reactor 2, you need to enforce those constraints for reactor 2. Right? You can think about f1 of x and f2 of x are those continuous constraints for the two reactors. Right? You have to at least select one of the reactor, either or all. Right? Now, here's the constraints you have. Right? You have y1 plus y2 equals to 1, meaning that you are selecting one of the two reactors. Right? If y1 is selected, then you are enforcing f1 of x. Right? This, when y1 equals to 1, this big M times 1 minus y1 equals to 0. Right? You are enforcing a constraint. And similarly, when reactor 2 is installed, you are enforcing the second constraint. Okay? So that's this so-called disjunction. You either enforce one constraint or another. Yes?
For each of those M's,
yeah.
They should be specific to, so one of those should be specific to F1.
Yeah, that's an excellent point, right? Yeah, so I'm being lazy to use a single notation, but they should be specific to F1 and F2, yeah. All right. Now, here's another application that occurs very frequently in some problems. How do you represent a discontinuous function? Right? It is very easy to think about. It's hard to optimize discontinuous function. At some point, there exists no gradient. Right? Like this function here. When x equals to 0, the c equals to 0. For example, maybe you have some equipment you want to build, right? The size of this equipment has to be at least L, and it cannot be bigger than U, right? Then if you are going to build this equipment, then the cost would be alpha plus beta x. You can think about alpha as a fixed cost of this equipment. No matter how large the size is, you have to pay alpha. Right? And beta is a variable cost. The larger this equipment is, the higher the cost, right? But then you cannot build this equipment to be outside the bounds L and U, right? So the function is represented as this function here. At x equal to 0, the cost is 0. Now the domain is not included between 0 and L, and then between L and U, you have a linear function, okay? So how do we represent this function? Well, you can introduce a binary variable to say, for example, if you are talking about equipment building, y will denote whether I'm building this equipment or not, right? If you are not building this equipment, you should force the cost to 0 and force x to 0, right? So here's what this constraint does. If y equals to 0, basically this go to 0, this go to 0, then you force x equals to 0, right? And then you also have the cost equal to 0, since you are not building the equipment, 0 fixed cost, and x is forced to 0, then you have 0 variable cost. Right? And then when y equals to 1, then you have x between size L and U. The cost is written as it is. Right? That's a way to represent a cost. In many applications, you have a cost term like this. Right? And usually you are minimizing cost, right? If you don't want to build this equipment, of course, y will just take the value 0. Right? Okay, so let me pause here before I introduce the next big topic to see if there are any questions. Right? So in the last few slides, we have given you a few examples using this, let's say, reactor example to motivate those linear inequalities. But sometimes there are even more complicated logic, right? Than if then, right? There could be any arbitrary complicated logic, right? So in the next few slides, what we will give you is a systematic way of translating any logic propositions into 0-1 variables and formulate them as mixed integer linear programs. Okay, right? So in order to do that, we need to introduce a concept called propositional logic. Okay? The idea of propositional logic is it can represent any logic relationships between logic variables, right? Suppose you have some logic variables that can take values true or false, right? I want to enforce some logic conditions or logic constraints among these variables, right? How do I use those notations to represent the logic, right? And then after I can represent them as logic conditions, how do I translate them into linear constraints using 0-1 variables? That's what we will do in the next few slides. Okay. Even if you haven't studied this before, I'm sure you heard about those notations maybe in some previous mathematics class, right? So this notation means logic OR, right? That means either A is true or B is true, or both of them are true, right? And this is logic AND, logic NOT, logic implication, exclusive OR. This is like equivalence or if and only if, right? So how do you actually represent or define those logic conditions? The way to define those conditions is through something called truth tables. Have you studied truth tables before in some previous class? Yeah. Okay, that's great. That makes my job much easier, right? So I will not cover each of these tables because that will take some time. Let's just pick a few of them, right? Now, if you consider logic OR, right, A or B, right, then with these conditions A or B, A and B can take in combination four different true or false combinations, right? When both A and B are true, then A or B will be true, right? When one of them is true, A or B is also true, right? When one of them is true. Only when both of them are false, then A or B becomes false. Right? That's what logic OR means. And that should be distinguished from something called exclusive OR. Right? So exclusive OR means if both A and B are true, then exclusive OR B will be false. Right? They cannot both be true. Right? And if one of them is true and false, and then exclusive OR B will be true. Okay. Now maybe we can talk about implication real quick. When A implies B, right? That means when A is true, then B must be true. Right? So here it satisfies this condition. When A is true, B is true, then A implies B is true, right? But then when A is true, B is false, then A implies B is false, right? Because when A is true, A implies B means B must be true, right? If A okay. And then when A is false, B can be either true or false. A implies B can both be true. Okay. Okay, so now with that, we have introduced some very basic, or you can think about this as unit logic operation, right? It's like your basic arithmetic operations when you play with numbers. Those are the basic operations you can play with for logic variables. And similar to arithmetic operators, we can introduce the calculus for logic operators. Right? So I will not go to prove all those calculus theorems. You can prove all these theorems using the truth table. Right? Just make sure the left truth table is the same as the right truth table. Right? Now, this thing is called De Morgan's theorem. Right? If you have A or B, but then I want to have a negation outside A or B, right? Then you have the negation of A, negation of B, but then you will replace the logic OR with the logic AND if you bring the negation inside, okay? And then if you do the negation of A and B, that becomes negation of A or negation of B, right? So the De Morgan theorem is like saying, if you want to bring the negation into a parenthesis, you are going to flip the AND and OR in these parentheses, okay? Now B and C are like the distributive law in calculus, right? If you have A and B or C, and then you want to eliminate these parentheses, what you will do is, bring this or inside. You have A or C and B or C, right? The AND will be moved here, and then you are bringing this or inside for both A and B. Okay. And similarly, you can do distribution of AND, right? How do you distribute AND C into, these parentheses? Then that will be A and C or B and C. Okay. What about implication? If we say A implies B, that means the negation of A or B, right? So A implies B means when A is true, then B must be true, right? Okay, so here, as you can see, if A is true, this guy is, the negation of A is false, right? Since it's an OR operator, B must be true, right? As if A is false, then B can take any values, right? You can easily say this thing is equivalent to the implication. Okay. Now, how do we represent logic as constraints? We actually have talked about most of them already, right? All those easy logic conditions can be easily translated into some linear equations. Here you just replace what is called the literal, right? So you can think about Pj as a literal. A literal is like a logic variable that can be true or false. And y is a binary variable that takes value 0, 1, right? So when this logic variable or the literal is true, then yj equals to 1. Otherwise, when the logic is false, then you represent yj equals to 0, right? So how do we translate all these logic conditions into linear equations or linear inequalities. What about not, right? If you have not Pj, right, then that means you can represent this as 1 minus yj, right? Because when Pj is true, yj equals to 1. When Pj is false, then essentially you have a 1 minus yj here, right? What about all when either Pj or Pi is true, then you basically have yi plus yj greater than 1, right? And if you have and, then that means both Pi and Pj must be true. Then this is saying yi equals to 1, yj equals to 1, right? Implication, right? If we have already said the implication is equivalent to negation of Pi or Pj, right? So here you have a negation and or, right? So you can combine what we've already covered in not and or to represent this condition, right? That means at least either 1 minus yi or yj is true, right? So the summation of 1 minus yi plus yj must be greater than or equal to 1. Okay. What about exclusive or? That means while Pi and Pj is true, right? So that will be yi plus yj equals to 1. Okay. And equivalent, that is simply yi equals to yj. Right. Any questions here? Okay, you can check again, right? If you have some doubts on this, you can just go back to the truth table and verify by yourself. Right? Okay. Now the question we will answer in the next few slides is, how do we represent general logic proposition using constraints, right? We've already represented all these basic logic conditions using constraints. And now if I give you some very complicated logic conditions, like this one, right? If P1 and P2 are both true, right? And then they implies P3 and P4, right? How do we represent this using linear inequalities? Then what about this, right? If Pf is true, then PD or and the negative Pm is true, right? So these are not so trivial to represent using linear inequalities, right? If you are very smart, you probably can inspect this for a while and then think about how to represent using linear inequalities, right? Or you can use the truth table and then by inspection, and then you sit there for a few tens of minutes and then you find a condition, right? But those would be a little bit arbitrary. It would be nice if we can have a systematic method for converting any logic conditions into linear inequalities, right? So that's what we will introduce in the next few slides, right? Give me any arbitrary logic conditions, I can always follow this recipe to convert them into linear inequalities, okay? So in order to do that, let's talk about a concept called functional completeness. Okay, so what does that mean? So the definition here is saying a set of logic operators is functionally complete if any logic propositions, or you can think about any truth table, can be constructed using only the operators from this set. Right? Suppose you want to represent some very complicated logic conditions, right? You may be wondering, how many operators do we need, right? We've introduced, if you check these slides, right? These many logic operators, right? Are those number of logic operators enough to represent any logic someone wants to represent? Or maybe there are too many, right? We don't even need all of them to represent any logic conditions, right? So this theorem is saying a set only consisting two logic operators, the AND operators and the NOT operators, is functionally complete, right? So that means as long as you have the AND operator and the NOT operator, you can essentially represent any logic conditions you want to represent, okay? That might be a little bit counterintuitive. You may think about, the and not operators are not so complicated, right? To show a rigorous proof, it will take a lot of time, but then we will just show you some intuition why this is true, right? So we will just show you why the logic operators or exclusive or implication equivalence can all be expressed using only and not operators, right? But then showing the logic, showing a rigorous proof of functional complete is not as trivial as this, right? We just give you some intuition why that is true. So here's a list. You can apply the and not operator to represent all the logic operations we've introduced before, right? So here, I'm not going through this whole list because that's a little bit tedious, right? If you are curious, you can read the whole list. I will just show you why this is true, right? The all operations A or B is equivalent to negation over negation A and negation of B, right? So why this is true? What is the theorem you need to use to show this is true? Yeah, exactly, right. De Morgan's theorem. De Morgan's theorem is you want to bring a negation into a parenthesis, right? Then when you bring this negation into the parenthesis, you will negate each of these literal separately, and then this and will be changed to an all, right? So that shows you a negation and and is sufficient to represent or, right? Similarly, you can show the exclusive or implication equivalence can also be replaced by negation and, okay? Yeah, so this theorem is saying like as long as you have and not, that's sufficient to represent any logic conditions, right? But in practice, as you can imagine, if you just have and not, it's not so intuitive, right? Whenever you want to represent implication, you need to replace implication by this very nasty formula, right? We may not want to just represent logic using and not. So therefore, we will show you a recipe where you can convert any logic propositions that include and, not, all, and implication into 0-1 inequalities, right? So usually with these three logic conditions, for most of the applications you encounter in practice, these four logic operators is enough, right, to represent any domain knowledge. Okay. Now let's start, right? How do we convert a logic condition that involves and, not, or, and implication into something that can be represented by 0-1 variables, right? So in order to do that, I will introduce a concept called conjunctive normal form, right? So our idea is just to give you a roadmap of what we are going to do, right? The idea is we will translate any logic propositions into this conjunctive normal form, right? The reason we want to translate any logic propositions into conjunctive normal form is conjunctive normal form has a very trivial way to be converted into 0-1 inequalities. Okay? And then if you can show there is a recipe to convert any logic propositions into C and F, then we are good to go. Okay? So let me first show you if I have some logic conditions already represented in C and F, how do we translate it into 0-1 variables? Okay. So a C and F is a following. You have basically a conjunction over a disjunction of literals, right? So a conjunction means you have and operator in the outer loop, right? You have in total J can be any arbitrary number, J conjunctions. And each of these conjunction is a disjunction over some literals. Okay. So let me give you an example, then it will be much easier to understand. Okay. So for example, this is a C and F, right? So outside the parentheses, I only have this and operator, right? There is no or operator outside the parentheses, right? And within each parenthesis, I only have the or operator. Right? So this is an OR operator, this is an OR operator. And then you may have some negation on some of the literals, right? You could do a negation on P2 and a negation on P1 here, right? So again, a conjunctive normal form is a conjunction over disjunctions, right? You have conjunctions or AND operators in the outer loop, and then within each of these parentheses, you have the OR operators only, right? I can give you maybe another, if you have, let's say, P1 or negation P2 or P3, and let's say negation of P2 or P3, right? This is also a conjunctive normal form, okay? Yeah, and you can add even more conjunctions, right? So any idea why this conjunctive normal form is easy to handle, right? How do you translate a conjunctive normal form into 0-1 inequalities? Right? If you look at this particular example, right? Let's say without looking at the answers I give, why it is easy to be translated into 0-1 inequalities.
Whatever we have and,
yeah.
just means we need to write as many equations.
Mm-hmm. Yeah.
That's like the first part. So
yeah.
we just need to look at each parenthesis and write whatever we have. And or
yeah.
is yeah, we have it on the slide, but
yeah.
1 plus
right.
Like the sum more or equal to.
Yeah, exactly. Right. You already got the key idea. The reason is if you have a conjunction, that means each of these disjunctions, right? Each of these clauses over the conjunction, each of them has to be true, right? In order for the conjunction to be true. If you have the AND over 10 different disjunctions, each of them have to hold separately. Right? If one of them is false, the AND will not hold. Right? So this thing has to be true, this thing has to be true, respectively, for the conjunctive normal form to hold true. Okay. And then each of these clauses is a disjunction, right? In order for the disjunction to hold, you just need at least one of them to be true, right? It's like the summation over these literals has to be greater than or equal to 1, right? If we were going to, let me erase this. We will use this example here, right? First of all, you could consider each of these logic in the parentheses, since they are different disjunctions over the end, right? So this thing has to hold, this thing has to hold, right? How do you translate the first disjunction into linear inequalities? That means either P1 is true or the negation of P2 is true, right? That means y1 plus 1 minus y2, because you have the negation of P2 here, that will be 1 minus y2. They have to be greater than or equal to 1, right? And for the second term, it's similar, right? You have negation of P1, that means 1 minus y1 plus y3 has to be greater than or equal to 1 for the second disjunction to hold. And then these two equations have to hold respectively because you have the conjunction and here in order for them to hold. Okay. Yeah, and then you can simplify them into this easier represented form. Okay. Yeah, I don't have the general representation, but yeah. So here I do have a general scheme, right? So each of these I is a literal, either a proposition or it's a negation, right? And then let's say each proposition is represented by the binary variable yi, right? When y is 1, pi is true, then y is 0, pi is false, right? The negation can be represented by 1 minus yi. Okay. Now since you have a disjunction over, each of these terms is a disjunction over, let's say I sub I, it can be translated into this constraint, the summation over yi prime is greater than or equal to 1, where yi prime corresponds to yi for non-negated pi, and 1 minus yi for negated pi. Right? So the summation over this, all those literals over the disjunction has to be greater than or equal to 1. Okay. Now, so hopefully it is clear conjunctive normal form can be easily translated into 0, 1 inequalities, right? Now the next question we need to answer is, if I give you any arbitrary logic proposition, right, how do you translate it into conjunctive normal form? Okay, so here's the recipe in 3 steps. The first step is removing the implications. If you have implications A implies B, you can use this relation to translate implication into negation and or, right? Because in conjunctive normal form, there is no implication. First thing you want to do is getting rid of the implication. Right? Then the second thing to think about is in conjunctive normal form, the negation is within the parentheses, right? There is no negation outside, right? All the negations are associated with the logic variables or the literals, right? So therefore, you should apply De Morgan's theorem to bring the negations inside, right? Now, all the negations will be associated with each of these variables here, right? Now, we are still not at conjunctive normal form yet, because you need to have the or inside the parentheses and the and outside, right? But it may not be in that form. What you can do is to apply the distributive relationship to bring the all over the end, right? If you have or outside the parentheses, you can use distributive law to bring them inside, right? So after following these 3 very simple steps, you get a conjunctive normal form, right? And then you can apply the translation to translate into linear inequalities. Okay, so let's do a quick exercise, right? Again, I'm giving you a process synthesis problem, but even if you are not a chemical engineer, this logic should be quite simple, right? The logic is, if in a process synthesis problem, if we select flash, then select distillation and not membrane, right? So here, so flash is sort of related to distillation. That's why you select distillation, not membrane, right? The logic is the following, right? PF represents flash, right? So if you select flash, that means that implies you should select distillation represented by PD and not membrane. PM represents selecting membrane, right? So it says not membrane. That's what this logic condition says. Right? How do you translate this logic condition into linear inequalities, right? Again, first step is removing the implication, right? You could apply this formula to replace the implication that will be PF is false or this term here, right? And then the second step is there is no need to apply De Morgan's law, right? The negation is already associated with each of the variable. You don't need to apply De Morgan's law. Then therefore the only step you need to apply is the distributive law to bring the logic all into the parentheses and bring the and outside, right? So now you apply that, you arrive at this CNF form. Right. So how do you translate the CNF into linear inequalities? That is very easy, right? So you have negation of PF or PD. That means either 1 minus F or YD is true. Their summation has to be greater than or equal to 1. And same wise, you can translate these logic conditions into linear inequalities. Okay, so here's what you can obtain. Again, if you are really smart, you probably don't need this recipe. Just by looking at this natural language claim, you are already good enough to translate that into 0, 1 variables. But maybe for some of the more complicated logic, you will struggle, right? This just gives you a very systematic way to represent any logic conditions into 0, 1 variables. Okay. Now, now I think I've covered the most important stuff I wanted to cover. Here, I want to cover something called the linear disjunctions. It's kind of unrelated to the logic variables. So the idea of linear disjunctions is sort of applying some logic conditions to sets. Right? So what I want to express here is I have some continuous variable x, right, represented in dimension Rn. Right? Now I want to express some logic condition that involve continuous variable. I want to say the continuous variable is either in this polyhedral set or in this polyhedral set. Right? So it is a union of two polyhedral sets. Right? So it is a logic OR over disjoint linear inequalities. Right? Either x is in this left-hand side set or the right-hand side set, right? And clearly, this feasible region is non-convex, right? You are either in this set or in that set. Nothing, there's a lot of empty things in between, right? It's not a convex set. So how do you represent these disjunctions over linear inequalities as mixed integer linear programming constraint? So that is an area called disjunctive programming that was introduced by Professor Egon Balázs in the 1960s. Right? So Professor Balázs was one of my professors at Carnegie Mellon. When I took his class, he was already 96 years old. So he was still standing there to teach a class for 1.5 hours on disjunctive programming. And then I think 2 weeks before he passed away at the age of 97, he was still teaching a class on convex polyhedral. And then we were one of the last batch of his students taking that class. And then his life experience is quite inspiring because he's like living 3 different lives. He was he was involved in the World War II when he was in Romania, I think. And then he was in prison during World War II. And then after the World War II, he was involved with the Romanian Communist Party. And then, he was put in jail as well, right? And then I think he got his PhD when he was really old, maybe like 50-year-old or something. And then he has a book about his life experience as well. It's called The Will to Freedom. You can purchase that book on Amazon if you are curious about his life experience. So anyways, he started working on optimization when he was pretty old. And then he was brought to the US by George Danzig, actually, when George Danzig was the one who invented the simplex algorithm, right? The reason is, I guess Danzig read his papers when Balázs was not in the US. I think he was put in prison, right? And then I think Danzig was able to contact the State Department in the U.S. and was able to bring Balázs here to the U.S. It was a quite inspiring figure, right? So he invented this thing called disjunctive programming when I think it's after he was in the U.S. already in 1960s, right? So that's one of the reasons we taught disjunctive programming in this class, because a lot of actually my PhD advisor was heavily influenced by Egon Balázs. He was able to translate disjunctive programming into something more general called generalized disjunctive programming. Then that shows to be very effective, especially in modeling chemical engineering problems, like problems in process design and process synthesis. Right? That's just a side note or a fun fact for you. Okay, yeah. Then again, so the simplest form of disjunctive programming is modeling union of polyhedral set. Right. So here you have a union over some polyhedral set, right? So each of these set is represented by AX less than or equal to B, right? And then you have a finite set of polyhedral, right? So then you could say X is in at least one of these polyhedral sets, right? Now here's a very simple example to explain what can be modeled using linear disjunctions, right? For some scheduling problem, right? A scheduling problem is just you have a number of tasks, then the task can be assigned to some machines to be processed. You want to schedule which task goes first, which goes second, and so forth, right? So if it says a common condition is either job A start before job B or job B start before job A, right? They can, if you have a single machine, they cannot happen at the same time. Now, if you have the start time TA and TB for job A and B, and the processing time for PA and PB, right? Processing time are parameters, right? You cannot change the processing time of a job on a given machine. And the start time are some variables you want to model, right? So the condition is that either A happens before B or B happens before A, right? So the left-hand side is saying TB has to be greater than or equal to TA plus PA, right? That means B happens before A, right? B can only start after job A is being processed, right? So if A start at this time T of A, right, then B cannot start until, let's say, the processing time of job A is PA, right? So after the machine processes the job, then B can start, right? So that's what this constraint means. And similarly, if B starts before A, that will be TB plus PB less than or equal to TA. Okay. Yeah. So that's a simple example of linear disjunctions, right? Either this inequality hold or the other inequality hold. Okay. Now the question is, how do you formulate linear disjunctions using mixed integer linear programming constraints, right? The one of the formulation is so-called big M reformulation, right? The idea is to assign each disjunct a binary variable, right? If a binary variable yj is equals to 1, that means x is in the j's polyhedral set, right? And yj is equal to 0 otherwise, okay? So now the idea is the summation of all the yj equals to 1, right? That means you are choosing one disjunct from in total, let's assume there are d disjuncts, right? Only one of the yj is chosen. When one of the yj is chosen, then this big M term will go to 0, and then the inequality has to hold, right? If the yj is not chosen, yj is 0, then you have an M that is big enough to make that inequality trivial for that particular problem, right? How to make that disjunction trivial? That means you need to pick M big enough such that this equation will include all the other disjuncts, right? So then you do not eliminate the possibility of satisfying other disjunct when yj is 0, right? So here, remember the big M is a vector here, since you can essentially have a large number of inequality constraints for each disjunct, right? And also, I keep reminding you that the key here is you should pick big M as small as possible. As long as you do not eliminate all the other disjuncts, then that's good enough. Okay. Any questions here? Yeah.
What's the trade-off for formulating this versus just the normal disjunctive program?
The normal disjunction program. Yeah. So the reason you want to formulate as this is you can use a mixed integer linear programming solver to solve this.
Yeah, but there might be some trade-off of writing it this way, right?
There is another way to write this problem as well. I will introduce in the next slide.
No, I mean like this is not equivalent to the original formulation.
this is equivalent to the original disjunctive programming. Because, I mean, if you write a problem like this, a solver for MILP solver will not take it, right?
Yeah.
You have to branch on the disjunctions. There are some solvers based on disjunctive programs.
So
But
like putting it in the big M formulation and not losing anything.
in losing anything in terms of feasibility, or?
Yeah,
Yeah.
like maybe might end up with something suboptimal, or the feasible set might be.
You are not losing anything in that sense. The optimal solution of the big M is still equivalent to this problem, since you know the big M do not. If the M is big enough, then it will not eliminate any feasible solutions of this problem, right? I mean, the feasible region is nothing but the X has to be either in this polyhedral or in that polyhedral. It cannot go outside of these two polyhedral set, right? If you use the big M and then you enforce the Y to be binary, right? Only one of these Y is true, right? So you are essentially enforcing one of these polyhedral constraints, right? So that's equivalent to the original problem. Yeah, whether the big M is a good formulation, that's another question, right? It may be a not so good a formulation, right? Okay. Yeah, so as I said, the big M may or may not be a good formulation, but most commonly people formulate disjunctions as big M because the solvers are very well fine-tuned on the big M constraints. It's very good at handling big M constraints, okay? So there's another formulation called convex Hall reformulation. I'm not going to the details, but the idea is you are introducing some zj variable for each of the disjuncts, right? Then here you still have the binary variables y, sum of yj equals to 1, right? And then if yj equals to 0, okay, then you will force the zj equals to 0, right? So you have some bounds on the zj variables, right? And x is a summation over all the zj variables, right? Because the summation of yj equals to 1, that means only one of these zj variable is non-zero, right? And then when yj is equal to 1, this inequality holds for the corresponding zj. Okay, that's an intuition. But you can rigorously prove that this convex Hall reformulation gives you the convex Hall of the disjunctive program. Okay, so what do I mean by that is, if you have a region saying that I'm either in this polyhedral set or in the second polyhedral set, right? In order to solve this problem, you need a convex relaxation in order to use some convex solvers, right? The tightest convex relaxation for this disjunctive set is a convex Hall of the two polyhedral set, right? The convex Hall is denoted by here, right? Remember, the convex Hall is essentially the smallest convex set you can have, right? That contains all the points in the disjunctive set. Right? So the convex Hall reformulation for this disjunction, for this disjunctive set, is the tightest convex set you can get, basically, right? But this is not a free lunch, right? As you can see, you are introducing a lot more variables than the big M reformulation, right? The trick here is that you need to introduce a continuous variable zj for each disjunct, right? In the big M, there is only one copy of the x variable. Here you need to introduce the same number of copies as a number of disjuncts in the convex Hall reformulation, right? So that's why I say this is not a free lunch, okay? Yeah, and then here I plotted the relaxation for the big M relaxation and the convex Hall relaxation, right? So if you relax a binary variable in big M, you could get a feasible region that is as large as this thing, right? It is a weaker reformulation than the convex Hall reformulation, okay? If you are curious, you could read, there is a textbook on disjunctive programming. Before Balash passed away, he wrote a book, so you could read that book. So here's an example. You could write the big M reformulation and the convex Hall reformulation as an exercise. I'm running out of time, so I won't go through those examples. Those will be good homework questions for you to practice. Okay. And then the reference is this textbook written by my PhD advisor, Professor Grossman, on advanced optimization for process systems engineering. You can take a look at the reference as well. Okay.